group strategy-proof mechanisms and cross-monotonic cost-sharing schemes. The cost-sharing problems defined in this chapter models the pricing problems for a service provided with a given set of customers. In settings where the demand is sensitive to the price and alternative choices for the service providers to conduct an auctions between the potential customers, to select the set of customers who can receive the service based on their willingness to pay and the cost structure of the problem. The goal is to design an auction mechanism that provides incentives for individuals as well as groups of agents to bid truthfully. In this section, we study this problem and exhibited its connections to cost sharing. We start with the definition of the setting. Let A be a set of an agent interested in receiving a service. The cost of providing service is given by a cost function, C, which maps from 2 to the A to R plus, the positive ration number union the single set 0, where C of S specifies the cost of providing service for agents in S. Each agent I has a value UI in R for receiving the service, that is, she is willing to pay at most UI to get the service. We further assume that the utility of agent I is given by UI times QI minus XI, where QI is an indicator variable that indicates whether she has received the service or not, and XI is the amount she has to pay. A cost-sharing mechanism is an algorithm that elicits a bid BI in R for each agent, and based on these bids decides which agents should receive the service and how much each of them has to pay. More formally, a cost-sharing mechanism is a function that associates to each vector B of bids a set Q of B, which is subset equals to A of agents to be serviced, and a vector P of B, which is in R to the n of payments. When there is no ambiguity, we write Q and P instead of Q of B and P of B, respectively. We assume that a mechanism satisfies the following conditions. No positive transfer, AMPT. The payments are non-negative. IEPI is greater than or equals to 0 for OI. Voluntary participation, VP. An agent who does not receive the service is not charged. IEPI equals to 0 for I which is not in Q. And an agent who receives the service is not charged more than her bid. IEPI which is less than or equals to BI for I in Q. The third one is consumer sovereignty. CS for each agent I, there is some bid BI star such that if I bid BI star, she will get the service no matter what others bid. Furthermore, we want the mechanisms to be approximately budget balanced. We call a mechanism gamma budget balanced with respect to the cost function C if the total amount of mechanism charges the agents is between gamma times C of Q and C of Q, i.e. gamma times C of Q is less than or equals to the summations of xi, summing for index I and Q, which is less than or equals to C of Q. We look for mechanisms called group strategy-proof mechanisms which satisfy the following property in addition to MPT, VP, and CS. Let S, which is subset equals to A, be a coalition of agents, and U prime be two vectors of bids satisfying UI equals to UI prime for OI not equals to S, not in S, and we think of U as the value of agents and U prime as a vector of strategically chosen bids. Let the pair QPB and Q prime B prime denote the outputs of the mechanism. When the bids are U and U prime respectively, a mechanism is group strategy proof if, for every coalition S of agents, if the inequality UI times QI prime minus BI prime is greater than or equals to UI times QI minus BI holds for every I in S, then it holds with equality for every I in S. In other words, there should not be any coalition S and vector U prime of bids such that if members of S announce U prime instead of U, their truth value as their bids, that every member of the coalition S is at least as happy as in the truthful scenario, and at least one person is happier. Mauling showed that cost-sharing method satisfies an additional property overturned cross-monotonicity can be used to design group strategy-proof cost-sharing mechanisms. The cross-monotonicity property captures the notion that agents should not be penalized as the service set grows. To define this property, we first need to define the notion of a cost-sharing scheme. Definition 15.12 Let AC denote a cost-sharing game. A cost-sharing scheme is a function that for each set S which is subset equals to A assigns a cost allocation for S. More formally, a cost-sharing scheme is a function C which maps from A times cross product 2 to the A maps to a rational number such that for every S which is subset equals to A and every I which is not in S, C of I S pair, the output of this function is 0. And we say that the cost-sharing scheme C is gamma budget balanced if for every set S which is subset equals to A, we have gamma times C of S, which is less than equals to the summations of C of IS, summing for index I in S, which is less than equals to C of S. Definition 15.13. A cost-sharing scheme C is cross-monotone if for all S and T which are subset or equals to A, and for all index I in S, C of IS is greater than equals to C of I and S union T. Okay, the mechanism. M of C. Initialize S, assign S with the A, and we repeat the following procedure. What is the following procedure of Malin's group strategy proof mechanism? We repeat the following. We let S be assigned with the set of index I in S such that BI which is greater than equals to C of IS, and until for all index I in S, BI is greater than equals to C of IS. And we return Q equals to S and PI equals to C of IS for all pairs of I, but for specific S. And the following proposition shows that cross-monotonicity is a strong property than core. Proposition 15.14. Let C be an gamma budget balanced cross-monotonic cost-sharing scheme for the cost-sharing game AC. Then C of dot any possible input of the first parameter and the second parameter is set A is in the gamma core of this game. Proof: we need to verify only that C of dot A satisfies the core property, i.e. for every set S which is subset equals to A, the summations of C of IA summing for all I in S is less than equals to C of S. By the cross-monotonicity property, for every I in S, C of IA is less than equals to C of IS. Therefore, the summations of C of IA summing for index I in S is less than equals to the summations of C of IS summing for index I in S, which is definitely less than equals to C of S, where the last inequality follows from the gamma budget balance property of C. Given a cross-monotonic cost-sharing scheme C for the cost-sharing game AC, we define a cost-sharing mechanism MC as presented in the figure 15.2. The following proposition provides an alternative way to view the mechanism MC. Proposition 15.15. Assume C is a cross-monotonic cost-sharing scheme for the cost-sharing game.
Welcome to Terminal 2.
The cost-sharing game AC and BI is in R plus union the singleton set 0, which means is a non-negative rational number for every I in A. Then there is a unique maxima set S, which is subset equals to A, satisfying the property that for every I in S, BI is greater than equals to C of IS. The mechanism MC returns this set. Proof: assume that two different maxima sets S1 and S2 satisfy the stated property, i.e. BI is greater than equals to C of I S1 for every I in S1, and BI is greater than equals to C of I S2 for every I in S2. Then, for every I in S1, BI is greater than equals to C of I S1, which is greater than equals to C of I S1 union S2, where the last inequality follows from a cross-monotonicity of C. Similarly, for every I in S2, Bi is greater than or equals to C of I S1 union S2. Therefore, the set S1 union S2 also satisfies this property, and this contradicts with the maximality of S1 and S2. Let S star denote the unique maximal set satisfying Bi which is greater than or equals to C of I S star for all I in S star. We claim that MC never eliminates any of the agents in S star from the set S. Consider for contradiction the first step where it eliminates an agent I in S star from the set S. This means that we must have Bi which is less than C of IS. However, since S star which is subset equals to S, by cross-monotonicity we have C of IS which is less than or equals to C of IS star, and hence Bi is less than C of IS star, contradicting the definition of S star. Therefore, the set Q returned by MC contains S star. By maximality of S star, it cannot contain any other agent, that is, Q is equals to S star. We are now ready to prove the following theorem of Mauling. Theorem 15.16. If C is an Garma budget balanced cross-monotonic cost-sharing scheme, then MC is a group strategy proof and a Garma budget balanced. Proof assume for contradiction that there is a coalition T of agents that benefits from bidding according to the vector U prime instead of their true values U. Agents in T can be partitioned into two sets T plus and T minus based on whether their bid in U prime is greater than their bid in U or not. First, we claim that it can be assumed without the loss of generality that T prime is empty, i.e. agents cannot benefit from overbidding. To see this, we start from a bid vector where every agent in T bids according to U prime and others bid truthfully, and reduce the bids of the agents in T prime to their true value one by one. If at any step, e.g. when the bid of agent I in T plus is reduced from Ui prime to Ui, the outcome of the auction changes. Then, by proposition 15.15, I must be a winner when she bids according to U prime, and not a winner when she bids according to U. This means that Ui prime is greater than or equals to C of I Si, which is greater than Ui, where Si is the set of winners when I bid according to U prime. However, this means that the agent I must pay an amount greater than her true value in the scenario where every agent in T bids according to U prime. This is in a contradiction with the assumption that agents in T all benefit from the collusion. By this argument, the bid of every agent in T plus can be lowered to her true value without changing the outcome of the auction. Therefore, we assume, without loss of generality, that T plus is empty. Now let S prime and S denote the set of winners in the untruthful and the truthful scenarios, i.e. when agents bid according to U prime and U, respectively. As the bid of each agent in U prime is less than or equal to her bid in U, by proposition 15.15, S prime which is subset equals to S. By cross-monotonicity, this implies that the payment of each agent in the untruthful scenario is at least as much as her payment in the truthful scenario. Therefore, no agent can be strictly happier in the untruthful scenario than in the truthful scenario. Mauling's theorem shows that cross-monotonic cost-sharing schemes give rise to group strategy-proof mechanisms. An interesting question is whether the converse also holds, i.e., is there a way to construct a cross-monotonic cost-sharing scheme given a group strategy mechanism? The answer to this question is negative, unless the cost function is assumed to be submodular, as there are examples where a cost function has a group strategy-proof mechanism but no cross-monotonic cost-sharing scheme. A partial characterization of the cost-sharing schemes that correspond to group strategy-proof mechanisms in terms of a property called semi-cross monotonicity is known. However, finding a complete characterization of the cost-sharing schemes arising from group strategy-proof mechanisms remains an open question.